Hello everyone. So previously we had discussed on the Euler-Stoller, totient function algorithm, right? So today we'll be discussing on the topic Miller-Rabin primality test algorithm. Yep. Let's get into the definition part first. So let's see what the definition states here. So let's see. So what is it? What does the definition part say here? The Miller-Rabin primality test is a probabilistic algorithm that is used to determine whether a number is prime or composite. Whether a number is prime or composite. Simple. It works by testing a number's properties under modular exponentiation. It works by testing a number's properties under modular exponentiation, making it efficient for the large integers. So this one we have to keep in mind. Yeah, let's get into the explanation part now. So the algorithm checks if a number n is probably prime or definitely composite using the random basis. Yeah. The algorithm checks if a number n is probably prime or definitely composite using the random basis. Yeah. So let's write n minus 1 is equivalent to the 2 to the power of 2 to the power of r into d, where d is nothing but the odd, right? So the algorithm checks basically if the number is probably prime or definitely composite. Yeah. So using random basis they have given. Yep. So either we will be noticing that it will be this one prime or composite right at the end. So this is fine. Let's write n minus 1 is equivalent to the 2 to the power of r into d, where d is odd, the first thing. And next what we'll do, we'll pick a random base, nothing but a. Here a actually greater than 1 and a less than n minus 1. Just remember this one, random base. We are just picking the random base. So here it says the algorithm checks if the number is probably prime or definite composite using the random basis, right? So we are just picking the random base a here. This is fine. First 2 points are clear, I believe. Next, what we will do, we'll compute x. We'll compute x equals a to the power of d mod n. A to the power of d mod n. This is fine. Next, let's go with we'll be going with the if condition here. If x equals 1 or x equals n minus 1, the previous one, then it passes for this particular base. Yep. Otherwise, what we'll do, we'll repeatedly square x and check if it becomes n minus 1. Yeah. If not, n is this one composite actually. If not, n is composite. Yep. So we'll repeat for the multiple random bases to reduce the chance of false positives. Yep. That's what we'll be doing. The exact same thing what we discussed now within the explanation part, let's try to articulate in the form of code. Right now, let's start writing the algorithm. Yep. So first thing, let's go with this one. First, let's do one thing. Let me import here random actually. Yeah, let me import random. Next, let's write the function to perform modular exponentiation. Right. So I'll just go with def here, function name power. So this one I just did a, d, and n respectively. Right. So this is fine. Now let's set the result to 1. So meaning here we'll start with the result 1. Next, let's take the mod n to keep the numbers small. So this one will be a equals a modulo n. This is fine. The next one is let's go with a while loop while there are bits left in the d, meaning so I'll just go with a while d less than 0. While d less than 0, what we will do here, if the current bit is 1, then we will multiply and take the mod n, right? So I'll just go with if d modulo 2, if it is equivalent to the value 1, then we will multiply and take the mod n, meaning I'll just go with the result equals result into a modulo n, modulo n. So this is fine. The next part is let's go with a right shift t, nothing but we have to divide by 2, right? So I'll just go with d equals d by 2, right? This one I can just write it on this way. Sorry, d equals d by 2. Yep. So this is fine. Finally, what we'll do, let's square the a and mod n, right? So that's what we discussed. So this one will be a equals a into a modulo n actually, modulo n. So finally, we'll return the result, nothing but we have to return the final modular exponentiation result. Yep. So let's go with the return here. What we need to return? Result actually, result variable res. So this is fine. Next step, we are done with the function power actually. We wrote a function to perform the modular exponentiation. This is fine. Now let's go with a Miller-Rabin test for a given base a, right? So let's go with the function here, Miller Rabin. So this one will be D comma N. Yep, this is fine. So within this helper method Miller test actually. So this one instead of the Rabin. So I'll just go with a test actually. So let's do one thing. Write the name completely. So within the Miller test. So I'll just do one thing. Let's pick a random base in 2 comma n minus 2. So this one will be a equals not the race one. It has to be random. Random. But I'll just go with a random int. Yeah, random int here. Let me go from 2 comma n minus 2 would be better. Yeah. So we'll be going with a random base actually, right? So we are just picking a random base in 2 comma n minus 2. So this is fine. Next step, let's compute a to the power of d modulo n. So I can just write it in this way: x equals power, x equals power. So this one will be a comma d comma n. Yeah, a comma d comma n. Now let's do one thing. Let's go with a simple if condition here. If x is 1 or n minus 1, then it's probably prime. And then we have to return Boolean value true. So this one will be if x equals 1 or x equals this one n minus 1, then what we need to do actually, so we have to return true man. Yeah, so we have to return Boolean value true. Next, let's do one thing. Let's write the simple while loop here. So let's repeat squaring process here. So I'll just go with while d not equal to n minus 1. Then what shall we do actually? X, let me set this one to x into x actually. Yep, modulo n. So this is fine. Just give me a second here. 1 second. So let's do one thing. Now let's continue with this one. Double D actually. D equals D into 2. Right. So let's do one thing. Now if x becomes 1, then it is composite, right? So let's write the simple if condition. If x equals 1, then let's do one thing. Let's return false here. So I'll just go with return false. So this is fine. Yep. So this is fine. Next, what we will do, let's if x becomes n minus 1, then it's probably fine, right? So sorry, then it's probably prime. Did I say fine? It's probably this one prime actually. If x, if it is equivalent to the value n minus 1, this is fine. Then what we will do, this is fine. Let's return true actually. Then let's return true. So this is fine. Yeah. This is fine. Next, we are left with only one step. Otherwise, it is composite, right? So we have to return false in that case. Yeah. So I'll just go with false actually. So this is fine. Now, let's go with a main function Miller-Rabin primality test. So let's do one thing. Let's go with a main function Miller-Rabin primality test, right? So I'll just go with def. Let me go with is prime here. Is prime of let me go with n comma k equals 5. N comma k equals 5. So this is fine. Yep. So k is nothing but the number of test iterations. So this one, let me write the simple if condition. We have to handle the base cases, right? So if n less than or equal to 1, or n if it is equivalent to the 4, then what shall I do? Within the if condition, let me return false here. Let me return the Boolean value false here, right? So I'll just give here false. So this is fine. Hmm, what if n less than or equal to 3? If n less than or equal to 3, then we have to return what we need to return here. We have to return true actually. So this is fine. So 2 and 3 are prime itself, right? So 2 is the smallest prime. We know this, and 3 is also prime actually. We are just checking if n is less than or equal to 3. Yep. So then what we have to do, we have to return true. So this is fine, man. Next step is let's do one thing. Let's assign the variable d to n minus 1 here. So this is fine. So let's go with a while condition here. While d modulo 2 actually, if it is equivalent to the 0, while d modulo 2, if it is equivalent to the 0, nothing but factor n minus 1 as 2 to the power of r into d, then what we will do, we will be going with d equals d by 2, right? So d equals d by 2. This works, man. This works. Next, what shall I do? Let's go with a for loop. Yeah. So let's request the this one. Let's repeat the test k times. Yeah. So I'll just go with a for loop here. This is fine for underscore in range. So let me go with the range. So this is fine. K. Yep, let me pass the K. So this is fine. Let me go with a simple if condition. If not, let me pass the Miller test here. We have already written the Miller test function. Let me go with D and N. This is fine. And within the if condition, let's return false. Yeah, let's return false, right? So yep, the next test would be the next would be else we have to return true, probably prime if all the test passes, right? So I'll just go with return true here, right? So return true here. So this is fine. Yep. So this is it for the algo, man. This is it for the algo, right? So first we went with this one power for the modular exponentiation. Next we went with this one Miller test actually. Then we went with is prime main function, main Miller-Rabin function actually. This is fine. Now let's go with a very simple example. Let's go with the example usage. Let me consider n equals some random number. Let me consider 37. Yeah, this is fine. If is prime, so this one, if is prime of n, this is fine. So let me print something for the interactiveness, right? So I'll just go with f followed by this one. Within the this one, what do we call this one? Uh, we are going with the string interpolation. We have passed n, right? So this is fine. Is probably, I'll just give here probably prime. Yep. So this is good. Next, else what we'll do, let me go with the print here. Let me go with the print. Let me go with, again, let's make use of the string interpolation here. Let me pass n, else it is composite, right? I'll just go with the else it is composite. So basically Miller-Rabin, this one primality test is used to find whether the number is this one prime or composite actually. Yeah, you should be knowing this one at the end at least. Yeah, we have almost come to the ending part, right? So now this is fine. So this is it for the example usage as well. We have successfully written the algo as well as we went with a simple example, right? So now let me explain this one. What do we call? Um, 1 second. Yeah, yeah. So what's the output that we need to get here? So 37 is 37 a prime actually. 37 is prime, right? So we have to get, we are just going with is probably prime. So 37 is probably prime is the output that we need to get. 37 is not divisible by this one any number. You can just check. 37 is divisible by 1 end itself, right? So this is fine. 37 is probably fine. So here, basically first what happens accordingly with the algorithm, the code checks first n equals 37. Yeah, the code first checks n equals 37. So this is fine. Next, it decomposes 36. It decomposes 36 into 2 square into 9. 2 square into 9, nothing but, so d equals 9 here. So d equals 9 here in this case, right? Yeah. So here it decomposes 36 equals 2 square into 9, nothing but 2 to the power of 2 into 9. So d equals 9 here, right? So the next step would be random bases like 5 comma 7 etc. Random bases like 5 comma 7, this one etc. are chosen here, right? Each test checks modular exponentiation. Yeah, the first function that we have written. All random tests pass here because 37 is prime. No base finds the contradiction here. Hence, the program prints 37 as possibly prime. So this one, yeah, it passes all the test cases, and we have to get this one 37 is possibly prime, right? So this is fine, I believe. Yep. So let's check the same now. We have written the algorithm successfully. Let's check the same now. So let's do one thing. I'll keep control J Python followed by file name.py. Yeah, 37 is probably prime. We are getting the desired output, right? So we are done with this particular algo. Now let's do one thing. We have come to the end of this one, right? Algo. So let's do one thing. We are done with the Miller-Rabin primality test algorithm. So let me summarize whatever we have learned so far. Just try to remember these 3 or 4 points. So this is very important. You have to know this one at any cost, right? So Miller-Rabin is a probabilistic test actually. The first thing, Miller-Rabin is actually a probabilistic test. Just remember this. So it can say either it can be probably prime, but never definitely prime. Yeah. So that is one of the disadvantage. But Miller-Rabin is a probabilistic test actually. This is fine. It's very efficient for the large numbers, right? So basically its use case, it is used in the cryptography. Its use cases, it is used in the cryptography. Just remember this one. Yeah, this is fine. So next, let's move on with the third, this one main point here. So repeating the test with more bases reduces the probability of the error exponentially. Exponentially. Just remember this one. Yeah. So the fourth one here is, so it is widely used in RSA encryption use cases. It's widely used in RSA encryption, large key generation. It's also used in large key generation as well. Along with it, and it's used in the prime verification as well. Usually, it is used in the prime verification. Yeah. So just remember this one. Yep. So it is widely used in the RSA encryption, large key generation, and the prime verification. Yeah. These are some of the points I wanted to discuss with you guys. So this is very important. Yeah. So we are done with this particular algorithm. Yeah. Next, what we'll do, next we'll be discussing on the topic Pollard RHO factorization. Yeah. For now, this is it. Thanks for watching, guys.